The universe is a vast, mysterious and often baffling place. As our telescopes peer deeper into space and our scientific understanding evolves, we continue to uncover objects that defy everything we thought we knew about physics and cosmology. From rogue planets, wandering the cosmos without a home, to supermassive black holes that seemingly formed too quickly, these celestial phenomena challenge our understanding of the fundamental laws that govern reality. Some of these objects are so strange that they shouldn't exist based on our current models of the universe. They push the boundaries of what we know about gravity, time, space, and even the very fabric of reality itself. How do planets exist in the harshest of conditions? Why do we find stars that seem older than the universe? What is causing unexplained cosmic signals to reach us from billions of light years away? These questions remain at the forefront of astrophysics, and with each new discovery, the universe becomes even more enigmatic. This exploration will take us on a journey through the strangest objects ever discovered, phenomena so bizarre that they baffle scientists to this day. As we venture into the unknown, we will encounter rogue planets, mysterious voids, impossible stars, and signals from the depths of space that may be more than they appear. One thing is certain: the deeper we look, the weirder the universe gets. And perhaps, somewhere in these cosmic anomalies lies the key to unlocking the greatest mysteries of existence. Rogue planets, worlds without a home. Imagine a planet floating alone in the darkness of space, untethered from any star, wandering the cosmos in eternal night. These are rogue planets, and they are some of the strangest objects in the universe. Unlike planets that orbit stars, rogue planets drift freely through space, ejected from their home systems or possibly formed independently in the void. Their existence challenges our understanding of planetary formation and raises fascinating questions about the possibility of life in the most extreme environments. What are rogue planets? A rogue planet is a planetary mass object that is not gravitationally bound to any star. Instead of orbiting a sun-like host, these planets move independently through the galaxy, completely isolated. Scientists estimate that rogue planets may actually outnumber stars in the Milky Way, with billions of them drifting unseen in the darkness. These planets are believed to form in protoplanetary disks, clouds of gas and dust surrounding young stars, just like regular planets. However, violent gravitational interactions can sometimes fling them out of their solar systems, sending them into interstellar space. Others may form directly from collapsing clouds of gas, much like stars, but without enough mass to ignite nuclear fusion. How do planets get ejected from their star systems? Rogue planets often become homeless due to chaotic gravitational events within their solar systems. Some common ways a planet can be ejected include gravitational interactions with giant planets. In young planetary systems, massive gas giants like Jupiter and Saturn can disrupt the orbits of smaller planets, flinging them out into space. Another way is through close encounters with other stars. If another star passes too close to a planetary system, its gravity can destabilize planetary orbits, ejecting planets into interstellar space. Finally, supernova explosions play a role. If a planet orbits a massive star that goes supernova, the sudden loss of mass can cause the planet to be thrown away at incredible speeds. Could rogue planets harbor life? At first glance, rogue planets might seem like the worst places for life to exist. Without a sun to provide warmth, their surfaces are shrouded in perpetual darkness, with temperatures plummeting to extreme lows. However, some scientists believe that certain rogue planets might still sustain life under the right conditions. Internal heating from a molten core, just like Earth, could provide heat for subsurface oceans, similar to what we see on moons like Europa and Enceladus. Additionally, thick atmospheres and greenhouse effects could play a part. A thick atmosphere rich in hydrogen could trap enough heat to maintain liquid water on the surface, even in deep space. Lastly, subsurface oceans are a possibility. If a rogue planet has a thick ice shell, heat from the core could maintain a liquid ocean beneath the surface, potentially providing a habitat for microbial life. Though rogue planets are difficult to detect because they emit almost no light, scientists have found several candidates using gravitational microlensing, a technique that observes how these objects bend the light of background stars. Some of the most notable discoveries include Ogle 2016 BLG 1928, one of the smallest rogue planets ever found, likely Earth-sized, discovered using microlensing. CFTOB, a possible rogue planet that appears to be floating freely rather than orbiting a star. PSOJ 318.5-22, a massive rogue planet about 6.5 times the mass of Jupiter, drifting 80 light-years away from Earth. As telescopes become more advanced, astronomers hope to uncover even more rogue planets and study their atmospheres. Future missions such as the Nancy Grace Roman Space Telescope and potential interstellar probes could help us understand whether these lonely worlds could support life. Rogue planets are proof that the universe is far stranger than we once believed. They exist in the most unexpected places, challenging our understanding of planetary formation and survival. Could one of these wandering worlds hold the key to extraterrestrial life? The search continues. Neutron stars are some of the most extreme objects in the universe. Born from the explosive deaths of massive stars, these ultra-dense remnants pack more mass than the Sun into a sphere barely the size of a city. The physics governing these strange objects defies common intuition. Matter is crushed to a state so exotic that it challenges our understanding of the fundamental forces of nature. Some neutron stars spin at unimaginable speeds, while others generate the strongest magnetic fields in the known universe. Their bizarre properties make them not just fascinating cosmic anomalies, but also crucial laboratories for studying the laws of physics under the most extreme conditions. Neutron stars form in the final moments of a massive star's life. When a star at least 8 times the mass of the Sun reaches the end of its nuclear fuel, it undergoes a supernova explosion. The outer layers are blasted into space, while the core collapses under its own gravity. If the collapsing core has between 1.4 and 2.3 times the mass of the Sun, it does not form a black hole but instead compresses into a neutron star. To understand how extreme this is, imagine compressing an entire mountain into a sugar cube, except even that doesn't match the density of a neutron star. A single teaspoon of neutron star material would weigh about 1 billion tons, as much as a mountain on Earth. Neutron stars exhibit some of the most extreme properties known in physics. Unimaginable density. The matter inside a neutron star is packed so tightly that atomic nuclei dissolve, forming a soup of neutrons and other subatomic particles. The core may even contain quark matter, a state of matter not found anywhere else in the universe. Incredible gravity. The gravitational pull on the surface of a neutron star is about 2 billion times stronger than Earth's gravity. If you were to stand on a neutron star, which is impossible, you would be instantly crushed into a thin layer of atoms. Extreme rotation speeds. Some neutron stars, called pulsars, spin at incredible rates, sometimes up to 700 times per second. This rapid rotation is due to the conservation of angular momentum from the original collapsing star. The strongest magnetic fields in the universe, certain neutron stars, known as magnetars, have magnetic fields a quadrillion times stronger than Earth's. These magnetic fields are so intense that they can distort atomic structures and even affect the vacuum of space itself. Pulsars, the universe's cosmic lighthouses. Pulsars are rapidly spinning neutron stars that emit beams of electromagnetic radiation from their magnetic poles. These beams sweep across space like the light from a lighthouse, creating a precise and regular blinking effect when observed from Earth. First discovered in 1967 by astronomer Jocelyn Bell Burnell, pulsars were initially thought to be signals from extraterrestrial civilizations and were jokingly nicknamed LGM, Little Green Men. The fastest known pulsar, PSRJ 1748-2446 AD, spins at 716 times per second, meaning its surface moves at nearly a quarter the speed of light. Magnetars, the most magnetic objects ever found. Magnetars are neutron stars with magnetic fields thousands of times stronger than normal neutron stars. These objects occasionally release violent bursts of energy, capable of disrupting satellites and even affecting Earth's ionosphere from thousands of light years away. In 2004, a magnetar burst from SGR 1806-20 released more energy in a fraction of a second than the Sun emits in 150,000 years. Despite decades of research, neutron stars remain one of the biggest mysteries in astrophysics. Scientists are still trying to understand what happens inside a neutron star's core. Does it contain exotic matter like quarks or even something stranger? Can neutron stars merge to create black holes? The detection of gravitational waves from neutron star collisions has confirmed that they can. But what happens in the milliseconds before a black hole forms is still unknown. Could neutron stars be used to test Einstein's theory of relativity? Their extreme gravity provides an excellent testing ground for general relativity and alternative theories of gravity. The strangest neutron stars ever discovered. While all neutron stars are bizarre, some are particularly mysterious. RxJ 1856.5-3754, a neutron star that appears too small for current models, suggesting it might be made of strange quark matter instead of neutrons. PSRB 1257+12, a pulsar that has planets orbiting it, making it one of the first known exoplanetary systems. J0030+0451. A neutron star whose surface is not perfectly spherical, hinting at unknown forces at play. Neutron stars are among the most fascinating and extreme objects in the universe. They challenge our understanding of physics, provide insights into the nature of matter under unimaginable pressures, and serve as cosmic laboratories for studying the fundamental forces of the universe. As telescopes and observatories continue to improve, future discoveries may reveal even stranger properties about these incredible objects. Could they hold the key to understanding dark matter, quantum gravity, or even the origin of the universe itself? One thing is certain, neutron stars will continue to surprise us. Black holes are among the most mysterious and terrifying objects in the universe. These cosmic behemoths are regions of space where gravity is so strong that nothing, not even light, can escape. While scientists have long predicted their existence through Einstein's theory of general relativity, black holes continue to defy our understanding of physics. Some are too big, too old, or too powerful to fit within our current models, challenging everything we know about the nature of time, space, and reality itself. In this section, we will explore the strangest, most inexplicable black holes ever discovered, from supermassive black holes that form too quickly to bizarre objects that seem to bend the laws of physics. A black hole is formed when a massive star collapses under its own gravity, creating a singularity, a point in space where matter is infinitely dense. Surrounding this singularity is the event horizon, the boundary beyond which nothing can escape. There are three main types of black holes: stellar mass black holes, formed from the collapse of a massive star. These typically range from 5 to 100 times the Sun's mass. Supermassive black holes, found at the centers of galaxies. These monsters contain millions to billions of solar masses. Their origins remain a mystery. Intermediate mass black holes, the missing link between stellar and supermassive black holes. These objects are extremely rare and difficult to detect. But here's where things get really weird. Some black holes in the universe shouldn't exist, based on our current understanding of how they form. Supermassive black holes are thought to form slowly over billions of years as they accumulate matter. However, astronomers have discovered black holes that are far too large for their age, meaning they must have grown at impossible speeds. Ton 618. This black hole, over 66 billion solar masses, is one of the largest ever discovered. Scientists have no idea how it got so massive in such a short time. Ulysses J 1342 plus 0928. A supermassive black hole found just 690 million years after the Big Bang, meaning it formed far too early for current growth models to explain. These objects suggest that black holes might grow through unknown mechanisms, possibly through direct collapse or even exotic physics we haven't yet discovered. Supermassive black holes are thought to form slowly over billions of years as they accumulate matter. However, astronomers have discovered black holes that are far too large for their age, meaning they must have grown at impossible speeds. Ton 618, this black hole, over 66 billion solar masses, is one of the largest ever discovered. Scientists have no idea how it got so massive in such a short time. Ulysses J 1342 plus 0928, a supermassive black hole found just 690 million years after the Big Bang, means it formed far too early for current growth models to explain. These objects suggest that black holes might grow through unknown mechanisms, possibly through direct collapse or even exotic physics we haven't yet discovered. In 2019, astronomers discovered LB1, a black hole in our galaxy with a mass of 70 times the Sun. According to standard models, stars in our region of the galaxy shouldn't be able to form black holes this massive. Scientists are still debating whether it is a single black hole or something even stranger. Black holes are known for pulling in everything that gets too close, but one black hole, V404 Cygni, has baffled scientists by ejecting matter in bizarre spiraling patterns, almost as if it were burping out chunks of material. This challenges our understanding of how black holes interact with their surroundings. In the galaxy OJ 287, astronomers have found two supermassive black holes locked in an orbit around each other. This discovery is important because it helps us understand how black holes merge, creating the gravitational waves we can now detect. One of the greatest mysteries of black holes is what happens beyond the event horizon. There are several possibilities. Singularity theory. At the center of a black hole, all matter is crushed into a single point of infinite density. This is where Einstein's equations break down. The firewall paradox. Some physicists propose that the event horizon is surrounded by an extremely hot firewall that destroys anything falling in. Wormhole possibility. A small group of scientists believe that black holes might be connected to other parts of the universe through wormholes, possibly allowing for interstellar travel. We currently lack the tools to test these ideas, but future research may reveal the true nature of what lies inside a black hole. Could we ever visit a black hole? While it is theoretically possible for a spacecraft to approach a black hole, any human attempting to cross the event horizon would experience spaghettification, a gruesome process where the gravitational pull on their feet is much stronger than on their head, stretching them into a thin strand of atoms. However, if certain theories hold true, a person falling into a black hole might experience time dilation, meaning time for them would slow down dramatically compared to an outside observer. In a strange way, they could see the distant future of the universe before being crushed at the singularity. Future telescopes, such as the Event Horizon Telescope and gravitational wave detectors, will continue to uncover their secrets. Some major questions remain. Did black holes help shape the early universe? Could black holes be made of dark matter? Do black holes hold the key to unifying quantum mechanics and general relativity? One thing is certain. The more we learn about black holes, the more mysterious they become. These cosmic monsters continue to defy our expectations, pushing the boundaries of what we know about space, time, and the very nature of reality. White holes, the opposite of black holes and the greatest cosmic mystery. White holes are one of the strangest theoretical objects in the universe, predicted by the same equations that describe black holes. While black holes pull everything in, never letting anything escape, white holes do the exact opposite. They are regions of space that nothing can enter, but instead, matter and energy are constantly ejected from them. If they exist, white holes could be among the most mysterious and unexplained objects in the cosmos, potentially rewriting our understanding of space, time, and even the origins of the universe itself. The concept of a white hole comes directly from Einstein's theory of general relativity, which allows for solutions that describe both black holes and their theoretical opposites. A black hole forms when a massive star collapses under its own gravity, creating a region of space where escape is impossible. But mathematical models suggest that if you reverse time, you get a white hole, an object that can never collapse and can never be entered, only exited. No one has ever observed a white hole, and their existence remains purely hypothetical, but some scientists believe they could explain some of the greatest mysteries in astrophysics. One of the most intriguing ideas is that white holes might be linked to black holes in a way that allows information or matter to travel between them. Some theories suggest that when matter falls into a black hole, instead of being lost forever, it could be ejected through a white hole in another part of the universe, or even in a completely different universe. This idea is similar to the concept of a wormhole, a hypothetical tunnel in space-time connecting distant points. If this were true, black holes might not be the ultimate dead ends we assume them to be, but instead strange gateways to unknown regions of space. There are also some researchers who speculate that the Big Bang itself might have been a white hole explosion. In this scenario, instead of the universe beginning from an infinitely small singularity, it could have been the result of matter ejected from a white hole in a parent universe. This idea is purely speculative, but offers a possible explanation for how our universe came into existence without requiring a singularity of infinite density, which current physics struggles to explain. Imagine a planet cold and dark, wandering alone through the endless void of space, with no sun to warm it and no solar system to anchor it. These are rogue planets, planetary bodies that have been ejected from their home systems and now drift aimlessly through the galaxy. Scientists estimate that there could be billions of rogue planets in our Milky Way alone, possibly even outnumbering stars. Their existence challenges our understanding of how planetary systems form and raises mind-bending questions about what kinds of life might be able to survive in such extreme environments. The first clue that rogue planets might exist came from observations of exoplanets, planets outside our solar system. As astronomers studied planetary systems beyond our own, they found that many appeared chaotic, with planets orbiting at odd angles in highly elliptical orbits, or even being flung outward by the gravitational interactions of larger worlds. This led to the idea that some planets might not just be pushed to the edges of their solar systems, but actually expelled into deep space. Directly detecting rogue planets is incredibly difficult because they emit almost no light. However, scientists have found them using a technique called gravitational microlensing, which occurs when a massive object passes in front of a distant star, briefly bending and magnifying its light. Through these observations, astronomers have identified multiple rogue planet candidates, some as large as Jupiter and others potentially Earth-sized. In 2021, researchers discovered what appears to be a free-floating planet roughly the size of Earth, suggesting that small, rocky rogue planets may be more common than we previously thought. The biggest mystery surrounding rogue planets is whether they can support life. Without a star, these planets lack the warmth that sustains ecosystems on Earth, but that doesn't necessarily mean they are lifeless. Some rogue planets may have thick atmospheres that trap heat, preventing them from freezing entirely. Others could harbour subsurface oceans, kept warm by the heat generated from radioactive decay in their cores, just like some of the icy moons in our solar system, such as Europa and Enceladus. If life can exist in the deep oceans of these moons, it's possible that similar life forms could survive in the hidden oceans of rogue planets. One particularly fascinating theory suggests that rogue planets could act as lifeboats for life, preserving organisms even after being ejected from their home solar systems. If a rogue planet had an advanced civilization before it was thrown into space, could they have survived the journey? While this might sound like science fiction, some researchers have speculated that rogue planets could be a possible way for life to spread between star systems, either through natural processes or through intelligent intervention. Another bizarre idea is that rogue planets could serve as stepping stones for interstellar travel. If humans or another intelligent species ever seek to colonize the galaxy, using rogue planets as waypoints could provide temporary bases, resources, and even protection from cosmic radiation. These worlds, hidden in the vast darkness of interstellar space, might become crucial for deep space exploration in the distant future. The study of rogue planets is still in its early stages, but new telescopes, such as the Nancy Grace Roman Space Telescope and the Vera C. Rubin Observatory, are expected to reveal many more of these mysterious worlds. Some might be frozen wastelands, others might hold deep hidden oceans, and a few could even harbor secrets about life's ability to endure in the harshest conditions imaginable. For now, rogue planets remain some of the strangest and most intriguing objects in the universe, dark, wandering enigmas that may one day change everything we know about planetary science and the potential for life beyond Earth. For decades, scientists have been searching for dark matter, an invisible substance that makes up roughly 85% of the universe's total mass. Though we cannot see or directly detect it, its gravitational influence shapes galaxies, bends light, and holds the cosmos together. But what if dark matter could do more than just exist in the shadows? Some physicists propose that in the early universe, dark matter may have clumped together to form a completely new type of celestial object, dark matter stars. If real, these hypothetical giants could challenge everything we thought we knew about how stars form, evolve, and die. Unlike ordinary stars, which shine by fusing hydrogen and helium in their cores, dark matter stars wouldn't rely on nuclear fusion at all. Instead, they would be powered by the annihilation of dark matter particles within them. According to some theories, dark matter could consist of weakly interacting massive particles, or WIMPs, that destroy each other upon collision, releasing enormous amounts of energy. If a cloud of dark matter were dense enough, this process could provide enough heat and light to create a massive glowing star, one that doesn't burn regular matter like the sun, but is instead fueled by dark matter interactions. If these strange objects existed, they would have been vastly different from any star we know today. Some calculations suggest that dark matter stars could have been millions of times more massive than our sun, with radii extending beyond our entire solar system. Unlike ordinary stars, which have lifespans dictated by their fuel supply, dark matter stars might have burned for far longer, perhaps even surviving until today. One of the biggest mysteries surrounding dark matter stars is whether they could have influenced the formation of the first galaxies. If such stars were present in the early universe, their massive energy output could have altered the surrounding environment, influencing how regular stars formed and even playing a role in shaping the structure of galaxies. Some researchers believe that the unusual brightness of certain early universe objects observed by the James Webb Space Telescope, or JWST, could hint at the possible existence of dark matter stars, but definitive proof remains elusive. Another mind-bending possibility is that dark matter stars could have acted as cradles for the formation of supermassive black holes. One of the greatest puzzles in astrophysics is how black holes as massive as those in the centers of galaxies formed so quickly after the Big Bang. Traditional models suggest that black holes grow by consuming gas and merging over billions of years, but some black holes in the early universe appear too large to have formed this way. If dark matter stars existed, they could have collapsed into enormous black holes, providing a shortcut for the formation of the supermassive black holes we observe today. But the most intriguing question of all is whether dark matter stars could have supported planets, and possibly even life. If a dark matter star emitted energy in a stable way, it could in theory provide heat to orbiting planets just as a normal star does. However, since these stars would be fundamentally different from anything we know, The conditions on their planets would be unlike anything found in conventional star systems. If intelligent life evolved around such a star, their understanding of physics and cosmology would be radically different from ours, potentially leading to an entirely alien way of perceiving the universe. Despite the fact that dark matter stars remain theoretical, they represent an exciting frontier in astrophysics. If future observations detect unusual, unexplained sources of light or heat that can't be linked to normal stars, we might have our first real evidence that these bizarre objects once existed, or perhaps even still do. For now, dark matter stars remain one of the strangest possibilities in the universe, challenging our understanding of the fundamental forces that shape the cosmos. In the search for extraterrestrial intelligence, one of the most fascinating ideas proposed is the existence of Dyson spheres, massive artificial structures built by advanced civilizations to harness the energy of their star. Originally proposed by physicist Freeman Dyson in 1960, a Dyson sphere is not a natural celestial object, but a theoretical megastructure that could, in theory, encase a star, capturing nearly all of its energy output to power an advanced society. If such structures exist, they would be among the strangest and most awe-inspiring objects in the universe, evidence of civilizations far beyond our own technological capabilities. The concept of a Dyson sphere stems from the idea that as civilizations progress, their energy needs grow exponentially. Humanity currently consumes energy from fossil fuels, nuclear power, and renewable sources, but a civilization thousands or millions of years more advanced might require the entire energy output of a star. The most efficient way to collect such energy would be to build a structure around the star itself, gathering its radiation and converting it into usable power. There are several variations of the Dyson sphere concept. The most extreme version is a solid shell completely enclosing a star, but such a structure would be nearly impossible to construct due to immense gravitational forces and structural instability. A more realistic approach is the Dyson swarm, an immense network of orbiting satellites or panels arranged around the star, collecting energy without fully enclosing it. Another possibility is a Dyson ring, a more limited structure similar to what we see in science fiction, like the Halo ring from the video game series. If Dyson spheres exist, they could be detectable from Earth. A star surrounded by a Dyson sphere would not emit visible light in the normal way, as its energy would be absorbed by the structure. Instead, it would likely radiate infrared heat as waste energy. Astronomers have already searched for such signals, and while no confirmed Dyson spheres have been found, some stars exhibit unusual dimming patterns that have sparked speculation. The most famous example is Tabby's star, CC 846852, which displays irregular and extreme brightness fluctuations that some researchers initially suggested could be caused by an incomplete Dyson swarm. However, more conventional explanations such as dust clouds remain more likely. If a civilization were advanced enough to build a Dyson sphere, it would likely be classified as a Type II civilization on the Kardashev scale, a system that ranks civilizations based on their energy consumption. A Type I civilization harnesses all the energy available on its home planet, something humanity has yet to achieve, while a Type II civilization can harness the full energy of a star. A Type III civilization would be capable of controlling energy on a galactic scale, possibly constructing Dyson spheres around multiple stars or even harvesting energy from black holes. One of the biggest mysteries surrounding Dyson spheres is whether humanity could ever build one. While current technology is nowhere near advanced enough, some scientists speculate that in the distant future we could construct a Dyson swarm using self-replicating robots that mine asteroids and build solar panels in orbit. If such a project were ever undertaken, it would represent the ultimate leap in our ability to harness energy, effectively making humanity a spacefaring interstellar species. The search for Dyson spheres continues, with new telescopes and infrared surveys scanning the cosmos for signs of artificial structures. If we ever discover one, it would be the clearest evidence yet that intelligent life exists elsewhere in the universe. Whether Dyson spheres are a reality or remain confined to the realm of speculation, they represent one of the most intriguing possibilities in astrophysics. The idea that somewhere out there, an ancient civilization may have already reshaped the stars themselves to fuel their technological ambitions. White holes, the theoretical cosmic phenomena that spit out matter. Black holes are among the most mysterious and terrifying objects in the universe, capable of swallowing anything that crosses their event horizon. But what if there were a cosmic counterpart? An object that does the opposite, ejecting matter instead of consuming it. Enter white holes, a theoretical concept predicted by Einstein's equations, but never observed in reality. If they exist, white holes would be some of the strangest and most unexplained objects in the cosmos, defying our understanding of space, time, and gravity. White holes are essentially time-reversed black holes. While a black hole's event horizon is a one-way entrance, where nothing, not even light, can escape, a white hole's event horizon would be a one-way exit, constantly expelling matter and energy while never allowing anything to enter. In theory, a white hole would look like an extremely bright object, radiating energy and pushing away anything that comes near it. However, unlike black holes, which form from the collapse of massive stars, there is no known physical process that could create a white hole, at least according to standard physics. The idea of white holes originates from the same equations that describe black holes. When solving Einstein's field equations, some solutions suggest that if you can have an infinitely dense singularity that pulls everything inward, a black hole, you can also have an infinitely dense singularity that expels everything outward, a white hole. Some scientists have speculated that white holes could be connected to black holes through wormholes, forming a bridge between different points in space or even different universes. One of the most controversial theories about white holes is that they might explain the Big Bang. The birth of our universe was an event in which an immense amount of matter and energy suddenly appeared, expanding rapidly into space. Some physicists have proposed that the Big Bang itself could have been a white hole eruption, possibly linked to the collapse of a black hole in another universe. In this scenario, black holes might not just destroy matter but recycle it, with white holes acting as cosmic fountains that spew out new galaxies, stars, and planets. Despite the theoretical appeal of white holes, there is currently no direct evidence that they exist. In fact, most physicists believe that real white holes are unlikely because they violate the second law of thermodynamics, which states that entropy, disorder, in the universe must always increase. A white hole would require a highly ordered state where all the energy and matter move outward in a precise way, something that seems almost impossible in the chaotic nature of the universe. However, some scientists speculate that we might have already observed white hole-like behavior in the form of certain unexplained cosmic events. Fast radio bursts, FRBs, mysterious millisecond-long pulses of radio waves from deep space, and high-energy gamma-ray bursts, the most powerful explosions in the universe, have characteristics that some have linked to white hole activity. While other explanations, such as magnetars and colliding neutron stars, are more widely accepted, the possibility remains that some of these extreme cosmic events could be signs of white holes momentarily flickering into existence. Even more mind-bending is the idea that cosmic strings could be cosmic shortcuts, linked to wormholes or acting as conduits between different regions of the universe. Some physicists suggest that if two cosmic strings moved past each other at near the speed of light, they could create a time-traveling loop, allowing for theoretical closed, time-like curves, a concept often explored in science fiction. If cosmic strings do exist, detecting them would be a monumental breakthrough in physics. Astronomers are actively searching for their signatures, looking for unusual gravitational lensing effects or disturbances in the cosmic microwave background. Some suggest that bursts of gravitational waves detected by LIGO and Virgo could even be caused by cosmic string vibrations, sending ripples through the fabric of space-time. The existence of cosmic strings remains unproven, but if they are real, they could unlock secrets about the early universe, the nature of space-time, and even the possibility of traversable wormholes. Whether they are relics of cosmic birth or powerful forces shaping galaxies, cosmic strings challenge our understanding of reality and hint at a universe stranger than we ever imagined. White holes, the opposite of black holes and the ultimate cosmic mystery. Some physicists believe in the theoretical concept of white holes, objects that are mathematically similar to black holes, but instead of pulling matter in, they violently eject everything out. If real white holes could be among the most bizarre and unexplored phenomena in the cosmos, possibly connected to black holes, wormholes, or even the origins of the universe itself. The idea of white holes comes from Einstein's general theory of relativity. Just as black holes form when massive stars collapse, white holes are theorized as the time-reversed solution to black hole equations. In other words, while nothing can escape from a black hole, nothing can enter a white hole. Only matter and energy can exit. This suggests that white holes would be highly unstable, spraying radiation and particles outward at near light speeds. Another possibility is that they might be hidden within the structure of black holes themselves. Some theories propose that when matter falls into a black hole, instead of being crushed into an infinitely dense singularity, it could be funneled through a bridge in space-time, a wormhole, and expelled somewhere else as a white hole. This would mean that black holes and white holes could be connected, acting like cosmic tunnels between different regions of space or even different universes. Some astrophysicists have suggested that white holes might explain mysterious cosmic events such as gamma-ray bursts, intensely powerful explosions that can outshine entire galaxies for brief moments. Could these be the dying echoes of white holes unleashing their final bursts of energy? Another radical idea is that the Big Bang itself was actually a gigantic white hole, expelling all the matter and energy that would eventually form the universe. If true, this would mean that our entire reality could be the result of a white hole's outburst. One of the biggest challenges with white holes is proving their existence. Unlike black holes, which can be detected through their immense gravitational effects, white holes might be much harder to observe, especially if they only exist for brief moments before collapsing. However, if scientists ever find one, it could revolutionize our understanding of gravity, space-time, and even the fate of the universe. If white holes are real, they could challenge everything we think we know about black holes, wormholes, and the structure of the cosmos. Are they gateways to other dimensions? Are they linked to the end of black holes, serving as the final stage in their life cycle? Or do they reveal something even deeper about the nature of time and reality? These questions remain unanswered, but the possibility of white holes reminds us that the universe may still have secrets that defy imagination. Planck stars, the possible end of black holes. Black holes are known for their terrifying ability to consume everything in their path, but what happens to the matter that falls inside? However, a radical new idea suggests a different fate. Instead of a singularity, the core of a black hole might transform into a Planck star, a theoretical object where quantum effects prevent total collapse, offering a potential solution to one of the biggest paradoxes in physics. The idea of Planck stars comes from loop quantum gravity, a theory that attempts to unify general relativity with quantum mechanics. In classical physics, black holes shrink endlessly as they radiate energy through Hawking radiation, eventually evaporating into nothing. But in loop quantum gravity, space-time is not infinitely divisible. It has a fundamental limit at the Planck scale, about 10 to the minus 35th meters, meaning that when a black hole shrinks down to this scale, quantum effects could cause it to bounce back instead of collapsing into a singularity. This bounce could create an ultra-dense but finite object known as a Planck star. This would solve the black hole information paradox, which asks what happens to the information of everything that falls into a black hole. Instead of being lost forever, as traditional physics suggests, that information might be stored and later released as the black hole transforms into a Planck star and radiates away. Another mind-bending possibility is that black holes could be reborn as white holes through this process. If a collapsing black hole transitions into a Planck star and then bounces back, it could reappear as a white hole, violently expelling all the matter and energy it had previously swallowed. This could mean that what we currently see as distant supernova explosions or gamma-ray bursts might actually be ancient black holes reaching the final stage of their life cycle and releasing everything they had consumed over billions of years. Detecting Planck stars would be incredibly difficult because they are predicted to be smaller than an atomic nucleus and hidden behind a black hole's event horizon. However, some scientists believe that if Planck stars eventually lead to bursts of radiation, we might be able to see their effects in high-energy cosmic events, such as unexplained gamma-ray flashes or unusual patterns in the cosmic microwave background. If proven to exist, Planck stars would revolutionize physics, offering a new understanding of black holes, quantum gravity, and the nature of the universe itself. Instead of being inescapable tombs, black holes might actually be cosmic rebirth engines, cycling matter and energy back into the universe through quantum processes we are only beginning to comprehend. This idea challenges the very fabric of modern astrophysics and suggests that even in the most extreme environments, the universe might still obey a deeper, hidden order. Magnetars, the universe's most extreme magnetic monsters. In the realm of dead stars, where physics is pushed to its absolute limits, magnetars stand out as some of the most extreme objects ever discovered. These ultra-dense neutron stars are only about 20 kilometers, roughly the size of a city, but contain more mass than our Sun and possess the most intense magnetic fields in the universe. With magnetic forces a quadrillion times stronger than Earth's, magnetars can warp space-time, unleash deadly radiation bursts, and even disrupt electronic devices from thousands of light-years away. Magnetars are a special type of neutron star which forms when a massive star explodes in a supernova but isn't quite massive enough to become a black hole. Normally, neutron stars already have incredibly high densities. Just a teaspoon of neutron star material would weigh around 1 billion tons. But in some rare cases, these neutron stars form with magnetic fields so powerful that they twist and deform the star's outer crust, causing massive starquakes that send waves of energy into space. The strength of a magnetar's magnetic field is beyond comprehension. If one were as close as the Moon, it would erase every credit card and hard drive on Earth just by disrupting their magnetic structures. Even at vast distances, these objects emit bursts of X-rays and gamma rays so powerful that they can be detected across galaxies. In 2004, a magnetar called SGR 1806-20 unleashed an explosion so intense that it briefly ionized Earth's atmosphere, despite being over 50,000 light-years away. This was the most powerful explosion ever recorded outside the solar system. What makes magnetars truly strange is their short lifespan. While normal neutron stars can last for billions of years, magnetars seem to survive only for around 10,000 years, a blink of an eye in cosmic terms. Their powerful magnetic fields eventually decay, and they either transform into regular neutron stars or collapse into black holes. Scientists still don't fully understand how they form or why only a small fraction of neutron stars become magnetars. Some researchers even speculate that magnetars could be linked to the mysterious fast radio bursts, FRBs, incredibly short but powerful bursts of radio waves that come from deep space. If true, magnetars might be behind some of the strangest unexplained signals in the universe, possibly even shedding light on phenomena like gamma-ray bursts and high-energy cosmic rays. Despite their rarity, magnetars remind us that the universe is filled with objects that defy our understanding of physics. These cosmic magnetic monsters are capable of reshaping their surroundings in ways no other known celestial body can, proving that even in death, some stars remain the most powerful forces in the cosmos. Dark matter stars, theoretical titans, powered by the invisible. For decades, scientists have been searching for the mysterious substance known as dark matter, an invisible and unknown form of mass that makes up about 85% of the universe's total matter. Though it does not emit, absorb, or reflect light, its presence is felt through its gravitational effects on galaxies. But what if dark matter isn't just floating around in halos around galaxies? What if, in the early universe, entire stars were made of it? This idea leads us to one of the strangest theoretical objects ever proposed: dark matter stars, gigantic glowing behemoths fueled by the unknown. The concept of dark matter stars, sometimes called dark stars, was introduced by physicists trying to understand what the very first stars in the universe might have looked like. Instead of being powered by nuclear fusion like our Sun, these hypothetical objects would have been powered by the annihilation of dark matter particles. This would have allowed them to grow hundreds, even thousands of times larger than normal stars, potentially reaching sizes as vast as millions of times the mass of our Sun. If these dark matter stars existed, they would have formed in the early universe, shortly after the Big Bang. Normal stars shine by fusing hydrogen into helium, releasing energy. But in dark matter stars, it's thought that weakly interacting massive particles, or WIMPs, a leading candidate for dark matter, could have been annihilating each other inside the star, releasing energy and keeping it from collapsing under its own gravity. This means that these stars could have lasted far longer than normal stars, possibly surviving hundreds of millions of years before eventually collapsing into black holes. One of the most fascinating ideas is that dark matter stars could be the ancestors of supermassive black holes. Today, we see black holes millions or even billions of times the mass of the Sun at the centers of galaxies. But it's still a mystery how they formed so quickly in the early universe. If dark matter stars grew large enough before collapsing, they could have directly seeded these cosmic giants, solving a long-standing astrophysical mystery. So, if dark matter stars existed in the early universe, could we detect their remnants today? Some scientists believe that their collapsed cores may still be lurking as exotic black holes with unique properties, or that traces of their former presence could be seen in cosmic background radiation. Others suggest that if they were still burning dark matter in some way, they could be hiding in deep space, appearing as faint, unusual stars, emitting strange excess heat. If confirmed, dark matter stars would change everything we know about stellar evolution, the early universe, and the nature of dark matter itself. They would suggest that the very first stars in the universe were unlike anything we see today, and that dark matter played a much bigger role in shaping the cosmos than we ever imagined. As scientists continue searching for the elusive nature of dark matter, the possibility of these invisible fueled titans remains one of the most intriguing cosmic mysteries. The universe is filled with objects so strange and extreme that they challenge our very understanding of physics. From the mind-bending physics of white holes and the quantum rebirth of Planck stars, to the terrifying power of magnetars and the hidden potential of dark matter stars. These cosmic anomalies reveal just how little we truly know about the forces shaping our reality. Each of these celestial mysteries defies conventional understanding, pushing the boundaries of science and inspiring new theories about the nature of space, time, and matter itself. What makes these objects even more fascinating is that many of them remain undiscovered or unproven. Some may exist only in mathematical equations, waiting for new telescopes and experiments to confirm their reality. Others, like magnetars, are very real but still poorly understood. And some, like dark matter stars, might be lurking in the depths of space, invisible yet influencing the structure of the cosmos in ways we have yet to comprehend. As technology advances, scientists are inching closer to unlocking these mysteries. Future space missions, next-generation telescopes and quantum physics breakthroughs could soon provide the evidence needed to confirm the existence of these strange objects. If we do, it could redefine our understanding of the universe and perhaps even our place within it. In the end, the most exciting part of astronomy and astrophysics is that there will always be more to discover. The cosmos is not only vast but also deeply mysterious, filled with phenomena that challenge our imagination and redefine the limits of what is possible. And as we continue to explore, one thing is certain: the universe will never cease to surprise us. Despite their presence in mathematical equations, there are major problems with the idea of white holes. The biggest challenge is explaining how they could form. Black holes form naturally from collapsing stars, but there is no known physical process that would create a white hole. If they exist, they must have been formed at the beginning of the universe or through some unknown mechanism beyond our current understanding of physics. Another issue is their stability. Most scientists believe that if a white hole did form, it would be incredibly unstable and would collapse into a black hole almost immediately. White holes remain one of the most fascinating and controversial topics in theoretical physics. Whether they exist or not, their potential implications are mind-boggling. If they are real, they could completely reshape our understanding of space and time, offering explanations for everything from the fate of information inside black holes to the origin of our universe. Future discoveries in quantum gravity and high-energy astrophysics may provide answers, but for now, white holes remain one of the greatest unsolved mysteries of the cosmos. Magnetars, the universe's most extreme magnetic monsters that shouldn't exist. A magnetar forms when a massive star goes supernova, leaving behind a neutron star. A collapsed core packed so densely that a sugar cube-sized piece of it would weigh as much as a mountain on Earth. While all neutron stars have strong magnetic fields, a magnetar's is orders of magnitude stronger, producing effects that seem almost supernatural. These fields are so intense that they can strip electrons from atoms and cause bizarre quantum interactions that scientists are only beginning to understand. One of the strangest things about magnetars is their sudden, violent bursts of energy. Every so often, a magnetar will unleash an explosion of X-rays and gamma rays that can outshine an entire galaxy for brief moments. In 2004, a magnetar in our own Milky Way, known as SGR 1806-20, released a flare so powerful that it affected Earth's atmosphere from over 50,000 light-years away. If such a burst were to occur closer to us, it could potentially disable satellites, damage power grids, and even disrupt human biology. The sheer energy of these events defies our understanding of how a neutron star could store and release such amounts of power. What's even stranger is that magnetars seem to be more common than our models predict. Based on current stellar evolution theories, only a very specific type of massive star should be able to form a magnetar, yet we keep finding them in unexpected places. Some are found where no massive stars should have been, while others have unusually long lifespans, contradicting the idea that their magnetic fields should decay relatively quickly. There are also magnetars that appear to be waking up from dormant states, suddenly reactivating after millions of years of silence, suggesting unknown physical processes at work. One of the most intriguing theories about magnetars is their potential link to fast radio bursts, mysterious, millisecond-long blasts of radio waves from deep space. While most FRBs remain unexplained, some have been directly traced back to magnetars, leading to speculation that these extreme stars might be responsible for many of the unexplained radio signals we detect from other galaxies. If magnetars are indeed the source of FRBs, it would mean they are capable of generating energy outputs comparable to entire stars, compressed into bursts lasting mere milliseconds. The question remains, how do magnetars get their extreme magnetic fields in the first place? One possibility is that they are born spinning incredibly fast, hundreds of times per second, creating a dynamo effect that amplifies their magnetism. Another theory suggests that magnetars might be created in rare supernova explosions that somehow preserve and enhance a star's magnetic properties rather than dispersing them. Some physicists even propose that magnetars could be harboring exotic states of matter, such as quark matter, or even strange matter, forms of ultra-dense material that could exist at the cores of these stars and contribute to their bizarre behavior. Understanding magnetars is crucial because they represent some of the most extreme physics in the universe. They challenge our knowledge of how stars live and die, how magnetism works on cosmic scales, and how energy can be stored and released in ways that defy conventional physics. Future telescopes and space missions will continue studying these strange objects. But for now, magnetars remain one of the most terrifying and inexplicable phenomena in the cosmos. Stellar ghosts with the power to reshape entire galaxies. Another mind-bending idea is that white holes might actually be what black holes turn into after they die. According to loop quantum gravity, a theory that attempts to unify quantum mechanics with general relativity, black holes don't just evaporate into nothingness as Hawking radiation predicts. Instead, they reach a critical point where they transform into white holes, expelling everything they had previously swallowed. If true, this could mean that in the far future, long after black holes have grown and consumed everything around them, they will eventually reverse their process and spill all that matter back into the universe in a spectacular cosmic rebirth. White holes remain purely theoretical, but they represent one of the most fascinating possibilities in modern physics. If they exist, they could change our understanding of black holes, the flow of time, and even the origins of our universe. Whether they are real or simply mathematical curiosities, the idea of white holes challenges our perception of reality itself, pushing the boundaries of what we think is possible in the vast and mysterious cosmos. Planets that shouldn't exist, the cosmic oddities that defy astronomical theories. For decades, astronomers believed they understood how planets formed. The process seemed straightforward. Clouds of gas and dust swirl around young stars, gradually clumping together into planets through gravity and collisions. But as we have discovered more and more exoplanets, planets outside our solar system, scientists have encountered objects that seem to break every rule, challenging our fundamental understanding of planetary formation. Some planets orbit their stars in impossible locations, while others have bizarre compositions that shouldn't be stable. These are the planets that, by all logic, simply shouldn't exist. One of the most baffling types of exoplanets is the hot Jupiter, a gas giant similar to Jupiter but orbiting extremely close to its star. In our solar system, Jupiter formed far from the Sun, where it was cold enough for gas to condense into a massive planet. Yet astronomers have found giant planets orbiting their stars at distances much closer than Mercury is to our Sun. At these extreme proximities, temperatures soar into the thousands of degrees, making it impossible for a gas giant to form naturally. The existence of hot Jupiters suggests that planets can migrate across solar systems, defying previous models that assumed planets form and stay where they originate. Even stranger are rogue planets, planets that don't orbit any star at all. These cosmic wanderers drift alone through the dark void of space, untethered to any sun. How did they get there? Some theories suggest that rogue planets were ejected from their home solar systems by gravitational interactions with larger planets. Others propose that they formed in isolation, without needing a star at all. What's even more fascinating is that some rogue planets might have thick atmospheres capable of trapping heat, potentially allowing for liquid water and even life to exist in the darkness of interstellar space. Another class of planets that defy expectations are super-Earths with extreme densities. Some of these planets are far denser than they should be based on their size, suggesting compositions that are almost entirely metal, with little to no rock or gas. Others have atmospheres so thick that they should have long since evaporated due to their proximity to their stars. One such example is TOI 849b, a planet so strange that scientists believe it might be the exposed core of a former gas giant. A Jupiter-like planet that somehow lost its entire atmosphere, leaving behind only its dense metallic heart. Perhaps the most mysterious of all are planets in the Neptunian desert. This is a region close to stars where we shouldn't find Neptune-sized planets, yet they exist. Planets of this size should either shrink due to atmospheric loss or grow into hot Jupiters by accumulating more gas. Yet some manage to survive in this hostile environment. How they manage to maintain their atmospheres in such extreme conditions remains one of the biggest mysteries in exoplanet research. And then there are the diamond planets. Planets that might be made almost entirely of carbon compressed into diamond under immense pressure. One candidate is 55 Cancri E, a super-Earth orbiting a star 40 light-years away. This planet's extreme heat, combined with its likely high carbon content, suggests that it could have a surface covered in graphite and diamonds. If such planets exist, they could hold untold riches. But mining them would be an impossible challenge given their immense gravity and extreme conditions. One of the most puzzling discoveries in recent years is the existence of planets orbiting pulsars, extremely dense remnants of dead stars that emit powerful beams of radiation. These environments are incredibly hostile, bathed in lethal radiation that should destroy any planet's atmosphere. Yet, against all odds, planets like PSRB 1257 plus 12b orbit pulsars, raising the question of how they formed and how they survived the explosive deaths of their parent stars. Some theories suggest that these planets formed after the supernova that created the pulsar, from the debris left behind, rather than surviving the original explosion. Each of these planetary oddities forces astronomers to rethink what they know about the universe. Every new discovery challenges established theories and suggests that planet formation is far more complex and chaotic than previously believed. As telescopes like the James Webb Space Telescope continue to uncover new worlds, we may soon find even stranger planets that push the limits of what we think is possible. The universe is full of surprises, and planets that shouldn't exist are proof that we still have so much more to learn. Dark matter stars, the hypothetical giants powered by the invisible. For decades, scientists have been trying to understand dark matter, the mysterious, invisible substance that makes up about 85% of the universe's total mass. It doesn't emit light, interact with normal matter in any significant way, or behave like anything we can directly observe. Yet its gravitational influence is undeniable. It holds galaxies together and shapes the cosmic web of the universe. But what if dark matter could do more than just invisibly influence the cosmos? What if in the early universe it actually powered entire stars? This is the idea behind dark matter stars, one of the most bizarre and unexplained possibilities in astrophysics. Unlike normal stars, which shine by fusing hydrogen into helium, dark matter stars would generate energy through an entirely different process: annihilation. Theoretical models suggest that in the early universe, clouds of normal matter may have mixed with concentrated pockets of dark matter. If this dark matter consisted of self-annihilating particles, meaning that when two dark matter particles collide, they destroy each other and release energy, then these regions could have ignited into massive glowing objects, sustained not by nuclear fusion, but by the destruction of dark matter itself. These hypothetical dark matter stars, sometimes called dark stars, would be unlike anything in the cosmos today. They could have been hundreds to thousands of times the size of the sun, burning with an eerie, diffuse glow rather than the concentrated brightness of ordinary stars. Because dark matter interactions are thought to be extremely weak, these stars wouldn't collapse into compact, dense objects like normal stars do. Instead, they could have remained incredibly large, spanning vast distances, while still producing energy for millions of years. One of the biggest questions surrounding dark matter stars is whether they ever actually existed. Some scientists believe they were only possible in the earliest stages of the universe, before normal stars fully took over. If they did form, they may have served as the precursors to supermassive black holes, the behemoths that now sit at the centers of galaxies. Since dark matter doesn't interact with light, these stars wouldn't leave behind the same kind of remnants that normal stars do, making them incredibly difficult to detect today. However, some astronomers have proposed that we might still be able to find evidence of dark matter stars. The James Webb Space Telescope has already detected some of the oldest and largest galaxies ever seen. And some objects at the farthest reaches of the observable universe appear larger and brighter than expected. Could these be signs of ancient dark matter stars? If so, they might provide a crucial missing link between the mysterious dark matter that fills the universe and the formation of the first black holes and galaxies. Even more mind-blowing is the possibility that dark matter stars could still exist today in some form. If regions of space contain enough dark matter, it's possible that some stars could still be partially powered by dark matter annihilation, allowing them to shine in unusual ways. Some scientists speculate that strange celestial objects with unexpected brightness profiles could be modern remnants of these ancient giants. If dark matter stars are real, they could completely change our understanding of how the first structures in the universe formed. They might explain how black holes became so massive so quickly, why some early galaxies are more developed than expected, and even give us new ways to study dark matter itself. The search for these cosmic phantoms is ongoing, and if astronomers can confirm their existence, it would be one of the greatest discoveries in astrophysics. A glimpse into a time when the universe was powered not just by ordinary matter, but by something far more mysterious and unseen. Cosmic strings, the universe's invisible fault lines. Among the strangest and most mind-bending ideas in physics is the concept of cosmic strings, hypothetical one-dimensional defects in space-time that could stretch across the entire universe. These objects, if they exist, would be thinner than an atomic nucleus, yet incredibly massive, with just a few kilometers of cosmic string outweighing the entire Earth. Some physicists believe cosmic strings are relics of the early universe, remnants from when space-time itself underwent fundamental phase transitions, similar to how cracks form in ice as water freezes. If real, cosmic strings could help explain the formation of galaxies, act as gravitational lenses, and even provide a pathway to time travel. The idea of cosmic strings comes from theoretical physics and cosmology, particularly from studies of how the universe evolved after the Big Bang. In the earliest moments of cosmic history, the universe was in a highly energetic, unified state. But as it expanded and cooled, different fundamental forces, such as electromagnetism and the strong nuclear force, separated from one another. This process might have left behind defects in space-time, cosmic strings being one such possibility. Imagine them as invisible cracks running across the universe, left over from its earliest moments. What makes cosmic strings so bizarre is their extreme gravitational effects. A single cosmic string, despite being incomprehensibly thin, would create an immense gravitational pull due to its high mass. If one passed through a solar system, it wouldn't behave like a planet or a star. It wouldn't bend light in the usual way or exert a typical gravitational influence. Instead, it would create a strange gravitational wake, distorting space-time around it like a stretched rubber band. This effect could bend light from distant stars and galaxies, creating unusual gravitational lensing effects that astronomers might be able to detect. Some scientists have even speculated that cosmic strings could be linked to time travel. Because of their extreme energy and gravitational properties, they could warp space-time in such a way that traveling along certain paths around them might theoretically allow an object to move backward in time. While this remains purely hypothetical, it's one of the more fascinating consequences of Einstein's general relativity equations. If cosmic strings exist, they could explain some of the largest structures in the universe. Some astronomers have suggested that these invisible filaments may have played a role in the formation of galaxies, acting as gravitational scaffolding around which matter accumulated. They might also be responsible for certain unexplained patterns in the cosmic microwave background radiation, the faint glow left over from the Big Bang. The challenge, of course, is finding them. Since cosmic strings are predicted to be incredibly thin and don't emit any light, they are nearly impossible to detect directly. However, their gravitational effects could be observable. Some astronomers have proposed searching for sudden shifts in the positions of stars or unusual lensing effects in deep space surveys. Others believe that cosmic strings, if they interact or oscillate, could emit bursts of gravitational waves, ripples in space-time that might be detectable with instruments like LIGO and Virgo. Despite decades of searching, no definitive evidence for cosmic strings has been found. Some theories suggest they might not exist at all, while others argue they could be much rarer than originally thought. However, the concept remains one of the most fascinating in theoretical physics, as it bridges the gap between particle physics, cosmology, and the fundamental structure of space-time. If we ever do find evidence of these invisible cosmic filaments, it would be one of the most groundbreaking discoveries in science, revealing new secrets about the fabric of the universe itself. Black holes are among the most well-known and mysterious objects in the universe. Their immense gravity traps everything, even light, making them cosmic prisons from which nothing can escape. But what if there was something that did the exact opposite? A cosmic object that nothing could enter, only expel from. This is the concept of a white hole, a theoretical object predicted by Einstein's equations, but never observed. If real, white holes could be time-reversed versions of black holes spewing out energy and matter instead of swallowing it. They challenge our understanding of space-time, and some scientists even believe they could be linked to the Big Bang or act as gateways to other universes. The idea of white holes emerges from general relativity, the same theory that predicts black holes. When physicists first explored Einstein's equations, they discovered that if you mathematically reverse the process of a black hole, where space-time collapses inward, you get a region of space where everything is ejected outward. Just as nothing can escape a black hole's event horizon, nothing could ever enter a white hole's event horizon. In other words, white holes would be cosmic fountains, endlessly spraying energy and matter into space. But there's a problem. While black holes can form naturally from the collapse of massive stars, there is no known process that would create a white hole. Black holes grow by consuming matter and merging with other black holes, but white holes would have to exist fully formed from the beginning. Something that doesn't fit with our current understanding of how the universe works. This is why many physicists consider white holes to be purely theoretical, solutions that exist in equations but not necessarily in reality. However, some scientists have proposed that white holes could actually be the end stage of black holes. According to one theory, when a black hole reaches the end of its life, perhaps due to quantum effects, it could transform into a white hole, expelling all the matter and energy it had swallowed over billions of years. This idea would help solve the information paradox, the problem of what happens to the information of objects that fall into black holes. If black holes eventually become white holes, it means nothing is truly lost. It's just stored until the transformation occurs. Another fascinating hypothesis suggests that our entire universe might be the result of a white hole explosion. Some physicists believe that the Big Bang itself resembles the mathematical properties of a white hole, where an immense amount of matter and energy suddenly appeared from a single point. If true, this would mean that white holes could create new universes, acting as cosmic birth chambers scattered throughout the multiverse. There are also speculations that white holes could be connected to wormholes, hypothetical tunnels through space-time that could act as shortcuts across the universe or even link different dimensions. If black holes suck in matter and white holes spit it out, some have suggested they might be two ends of the same cosmic bridge. This idea appears frequently in science fiction but remains highly speculative in actual physics. The biggest challenge in proving white holes exist is that we've never seen one. Unlike black holes, which can be detected through their gravitational effects, white holes would be incredibly unstable. If they formed, they might instantly explode or dissipate, making them nearly impossible to observe. Some astronomers have proposed that unexplained cosmic bursts, such as gamma-ray bursts or certain types of fast radio bursts, might be signs of white hole activity, but no solid evidence has been found. Despite their elusive nature, white holes remain one of the most intriguing possibilities in astrophysics. If we ever confirm their existence, they could revolutionize our understanding of time, space, and the fundamental laws governing the cosmos. They challenge the very nature of reality itself, hinting at a universe far stranger than we ever imagined. Magnetars, the most extreme magnetic monsters in the universe. Among the strangest and most terrifying objects in the cosmos are magnetars, ultra-dense remnants of dead stars with the most powerful magnetic fields known to exist. These exotic neutron stars pack more mass than our Sun into a sphere barely 20 kilometers across, and their magnetic fields are so intense that they could strip the atoms from your body from thousands of kilometers away. Magnetars challenge the limits of physics, and their sudden, violent outbursts can be detected across vast cosmic distances. Magnetars are a rare type of neutron star, which forms when a massive star collapses after a supernova. While most neutron stars rotate steadily and emit beams of radiation, as seen in pulsars, a small fraction of them develop magnetic fields a quadrillion times stronger than Earth's. These fields are so intense that they distort the very structure of atoms and can affect space itself, creating some of the most extreme environments in the known universe. What makes magnetars so strange is their unpredictable nature. Unlike regular neutron stars, magnetars experience starquakes, sudden shifts in their crust caused by the intense magnetic forces. These quakes can release enormous amounts of energy, causing powerful bursts of X-rays and gamma rays that can be detected from billions of light-years away. One such explosion, recorded in 2004, from a magnetar 50,000 light-years away, briefly outshone all the stars in the Milky Way combined. If a magnetar were just 10 light-years away, it could potentially wipe out Earth's atmosphere. Scientists still don't fully understand why some neutron stars become magnetars while others don't. One theory suggests that if a star is spinning fast enough when it collapses, it can generate a dynamo effect, amplifying its magnetic field to mind-boggling levels. Others propose that interactions with dark matter or exotic physics could be involved in their formation. Another bizarre possibility is that magnetars could be linked to fast radio bursts, or FRBs, mysterious, millisecond-long flashes of radio waves that come from deep space. Some magnetars have been observed emitting bursts of radio waves similar to FRBs, leading scientists to suspect they might be the source of some of these unexplained cosmic signals. Despite their destructive power, magnetars might also help unlock some of the biggest secrets of the universe. Their extreme magnetic fields could offer insights into quantum mechanics, exotic states of matter, and even the fundamental nature of space-time itself. They push the boundaries of what we think is possible, reminding us that the universe is full of strange and unexplained forces waiting to be understood. Among the greatest mysteries in astrophysics is dark matter, the invisible substance that makes up roughly 85% of the universe's mass, but does not interact with light or normal matter in any way we can directly observe. While dark matter is typically thought of as a diffuse halo surrounding galaxies, some scientists have proposed a radical idea. What if, in the early universe, dark matter could have formed stars? These hypothetical dark matter stars, also known as dark stars, challenge our understanding of stellar evolution and could explain some of the strangest cosmic observations. Dark matter stars would not be like ordinary stars that burn through nuclear fusion. Instead of fusing hydrogen into helium, these bizarre objects would be powered by the annihilation of dark matter particles within them. If dark matter consists of weakly interacting massive particles, or WIMPs as some theories suggest, then when these particles collide, they could self-annihilate, releasing enormous amounts of energy. This process could, in theory, allow a dark matter star to shine without ever igniting nuclear fusion. What makes dark matter stars truly strange is that they could have been enormous. Some models suggest they could have reached up to millions of times the mass of the Sun and spanned hundreds of times the Sun's radius. Unlike normal stars, which eventually burn out or explode in supernova, dark matter stars might have been able to sustain themselves for millions or even billions of years, depending on how much dark matter they contained. These hypothetical objects are believed to have formed during the very early universe, possibly before the first conventional stars. If they existed, they might have delayed the formation of ordinary stars by providing a different source of heat and energy. But as the universe evolved, dark matter stars would have eventually collapsed, potentially forming some of the first supermassive black holes, explaining how such giant black holes appeared so early in cosmic history. One of the most exciting aspects of the dark matter star hypothesis is that we might actually be able to find them. Some astronomers have proposed that certain unexplained cosmic observations, such as extremely bright and massive objects in the distant universe, could actually be dark matter stars. The James Webb Space Telescope, which can look deep into the early universe, might provide clues as to whether these objects ever existed. If dark matter stars were real, they could reshape our understanding of both cosmology and particle physics. Their existence would be direct evidence that dark matter interacts in ways beyond just gravity, and they might even help us unlock the true nature of this mysterious substance. They challenge the traditional definition of what a star is, and remind us that the universe may be far stranger than we ever imagined. While we have yet to find definitive proof of dark matter stars, the idea continues to intrigue scientists. If they existed in the past, remnants of their formation could still be hidden in the cosmos, waiting to be discovered. Cosmic strings, invisible threads that could rip the universe apart. Deep in the fabric of the cosmos, there may exist cosmic strings, infinitesimally thin but immensely dense structures stretching across space like relics from the birth of the universe. These theoretical objects, first proposed in the 1970s, are thought to be one-dimensional defects in space-time, left over from the violent phase transitions that occurred in the early universe. Unlike anything we can directly observe, cosmic strings could be thinner than an atom, yet more massive than an entire planet, making them some of the strangest and most extreme structures ever hypothesized. Cosmic strings are believed to form due to symmetry breaking, a process that occurs when the universe cools and fundamental forces separate. Just as cracks form in ice as water freezes, defects in space-time could have formed as the universe expanded. These defects, if they exist, would be cosmological in scale, stretching across entire galaxies and beyond, potentially even forming vast cosmic networks. What makes cosmic strings so bizarre is their incredible mass density. A segment of string just a mile long could weigh as much as Earth. Because of their extreme density, cosmic strings would exert tremendous gravitational effects, warping space-time around them. If one passed between you and a distant star, you would see the light from the star split into two, creating a unique gravitational lensing effect. Astronomers have searched for such signals, but so far no definitive evidence has been found. One of the most fascinating possibilities surrounding cosmic strings is their potential role in shaping the universe. Some theories suggest that these structures could have helped seed the formation of galaxies, providing the gravitational scaffolding for matter to accumulate. Others propose that cosmic strings might even be linked to black holes, with their immense energy possibly triggering the collapse of surrounding matter.